Alright, this is our second video on mean absolute deviation. So we learned yesterday that the mean absolute deviation is exactly what it sounds like. It's the average of the absolute deviation. And we learned that the absolute deviation is how far the data is from the mean of the data. So we learned a four-step process for doing this. The first thing we need to do is find the mean of the data. Then we find the distance between each data value and the mean. Then we find the sum of those distances and then divide to find the mean of that. Now, that again seems a little overwhelming at once. So what I'm going to do instead is I'm going to just show you some examples that have already been completed for you. So we're going to zoom in and focus on one at a time here. So we're going to take a look at just this one here. That's the price of textbooks. So we found these 10 prices of textbooks. When you're in college, you got to buy your own textbooks. They can get pretty expensive. We could find that the mean is 75. And once we found that mean, we found out how far the numbers that were the actual raw data, how far they were from the mean. So you can see that the $78 textbook was 3 away, and that's why that corresponding 3 went there. The $55 textbook was 20 away. You will note it doesn't matter which direction it is. That's where the term absolute comes in. It's just how far it is from the mean. So once we got that, we're going to add up all that data and then divide by 10, and that's where we got the mean absolute deviation of 17.4. We're going to look at another example here, which is the number of songs on an album. So, some albums have a lot more songs than others, and you can see that we took this data, these 10 albums, we got a mean of 10.5. Now, this was a decimal number, and that's okay. So our variation, our absolute deviation, was only by half of 1. So 10 and 10.5 are only 0.5 away. That's why that's the number here. And moving forward, you can see the 13 was 2.5 away, the 7 was 3.5 away. And what's interesting, as you look at it, both 10 and 11 are 0.5 away. Because again, it doesn't matter which direction it's in. But when it's all done, we found the average of the deviations, and that's what gave us our mean absolute deviation. So we're going to do an example here where we're just thinking about this information. It says that data set A has a mean absolute deviation of 16, and data set B has a mean absolute deviation of 3. What does this tell you? And what we're realizing is that just like with range and interquartile range, when we have a mean absolute deviation that is small, that indicates that the numbers are close to their mean. That's a single number that tells us that the data clusters close together, that it doesn't vary a lot. And again, that's what we're trying to do. When we have measures of variation, we want to be able to interpret that. And we should see that when our measure of variation is small, it tells me that the data is close together. So we're going to go ahead and look at some prices to get into different museums. So I'm sure many of you guys have been to museums. So in order to do this, I'm going to follow my steps. It asks me to find and interpret the range, interquartile range, and mean absolute deviation. These numbers are rather small. I'm going to rewrite them in order because that's going to help me for my range and my interquartile range. So I've got 11, 12, 15, 16, 20, 20, and 25. I got 1, 2, 3, 4, 5, 6, 7 numbers in my data. I've got 7 in my list. I very clearly can find my range by subtracting 25 and 11 to get a range of 14. All right. I can find my interquartile range by recognizing that this is the middle of my data. So this is my upper half. This is my lower half. This would be quartile 3, and this would be quartile 1. And so if I subtract quartile 3 minus quartile 1, I get an interquartile range of 8. Now, to find the mean absolute deviation, that might make you mad because it takes so long. If you get it there, it makes you mad. All right, what we're going to do is we're going to first add up all these numbers and find out their sum. So use my calculator here, and we'll add that up. 11 plus 12 plus 15 plus 16 plus 20 plus 20 plus 25 gives us 119. I'm going to go ahead and divide that by 7, and that gives us a mean of 17. So if our mean is 17, what we're going to do is we're going to see how far these numbers are from the mean. So this is 6 away, this is 5 away, this is 2 away, this is 1 away, this is 3, another 3, and then that one's 8 away. So now that I've got my absolute deviations, I'm going to go ahead and find out their mean. So 6 plus 5 plus 2 is 1. And that gave me a total of 28, which I divide by 7 again, and I get a mean absolute deviation of 4. Now, all three of these measures of variation, they let us know. The mean absolute deviation, I think, is the most telling here. It tells me my data is really close together, okay? In general, it's pretty close because everything's within 4 of the average. So that's good. Again, the smaller the mean absolute deviation, the closer the data is to center. Now, just being reasonable here, which of these jars do you think would have the greater mean absolute deviation? So people are going to be guessing how many gumballs are in the jar, and people are going to be guessing the number of baseballs in the jar. Yeah, obviously, the data is going to vary quite a bit with these guesses. People aren't going to really know how many gumballs are in that jar, and so the data is going to vary. We're going to have people guessing as few as, maybe 15 or 16, some people guessing something in the hundreds. Whereas this, it's pretty obvious there's 2 baseballs in that jar, and even if there is a couple more because they're big, your data is going to be pretty close. You're not going to have people guessing 100 there, all right? And so what we're going to realize is that when data is further spread out, it's going to have a greater mean absolute deviation.